Okay, good morning. What I want you to do is just make sure, you always start at 100%, and then as I mark, I deduct marks, just like Kramer when he starts with a stack of tips and then he takes it away. But what I want you to do is just double check, because I went a little fast when I was tallying, and so I want you to just double check that everything matches what it looks like. And if it doesn't, then just let me know after class or something, and I'll fix it. Here's hoping, right? Only because I caught one where I had written 6 instead of 16, and that makes a huge difference in the total. I'd hate to have done that twice. Okay, this one, I keep putting it off, and then I said, oh, I'll add it to the notes, blah, 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 and then I forgot to do that. So instead, for review, how about I just want to give you a little moment to work on it, because it's a little bit involved. Should I make them both bigger, maybe? Let's see here. I'm gonna try just to warm up here. And also I need to set up my laptop. Okay. There. You see the formula down there? Welcome to. Now? Phew. Good. Startling. You're welcome to talk it out, is what I was trying to say. But it is Monday morning, so I get it. boring recording this will be. Probably should have paused it. Is this thing on? Word problems, right? Can I scrunch them up again? A little bit. Got the deets. Okay. Good place to start is to list all the things that you have and then freak out about all the things you don't have. All right. And so let's see here. Okay, a dead body is found, fine. It was 85 degrees when it was found, okay? Which means that, okay, at some time point, well, I guess I should write out T of T is A times E to the KT plus TS, where TS is the surrounding temperature. So when it was found, it was 85 degrees. So T of something is 85. We'll start there. There's a sneaky thing we're gonna do. We're gonna call that 0. And then go backwards. We could get fancier and say that this time point is gonna be T minus however many, or plus, don't trip yourself up, Emily, T plus the time of death, or how long ago it was. But what we're gonna do is we're just gonna call this 0. And then now we're gonna talk about time relative to when we found the body. Time will be relative to when we found the body. Okay, great. After 30 minutes, the temperature is 82 degrees. So after 30 minutes of finding the body, right, so that makes T of 30, 82. The surrounding air temperature is 60, which means that TS is 60. Some of these are easier to identify than others, right? And then we want to find T, right, relative to 0, that makes the temperature 98.6, right? So we want to find T of T equal to 98.6. Okay. Usually, we like to leverage the T of 0. That'll let us solve for some things, but we've got TS as well. So let's just plug in what we know. So we have T of T is AE to the KT plus 60. And we said that T of 0, so when T is 0, we're going to force the temperature to be 85. So here we've got 85 is AE to the K times 0 plus 60. K times 0 is 0. E to the power of 0 is 1. So we have 85A, and I'll just show that, times 1 plus 60. I feel like that's not what I found before. Is this a jiving? What do I do? What did I do, rather?
I did for 82 equals 85 e to the t 30 to solve for k.
Yeah. But did you guys get A is 25? That's not what I got before. 85 minus 60. Oh man. I'll keep going, but 85 minus 60. Yeah. So when you have the no, because you've got the surrounding temperature and then the initial temperature already happened. Just have this feeling that I didn't have A equal to 25 before, but I have no way to check it.
98.6 instead of 85.
But I'm letting the 0 time point be when I found it. So later I'll use the 98 points. Okay, let's try it. We'll keep going. Okay. So then T of T is Any 5? Question mark. E to the kt plus 60. It's possible it's going to work out anyways. I'm going to use the 30 time point. T of 30 equals 82 in here. So T of 30 is 82. 82 is 25 e to the k times 30. Plus 60. So now, rusty calculator, 82 minus 60 is 22. And then divide by 25 in the next step, 30K. Because it works out to a nice number, I'll just write the decimal. E to the 30K. To solve for K, I'm going to take the natural log, same base. And so I've got the natural log of 0.88 is, just because we're warming up, the natural log of e to the 30K. But you're fine if you just want to write 30K. That's the whole point of taking the log, is to drop it down. Oh, I'm in the wrong. Uh-oh. Copy. Paste. There. It's in the wrong day. Okay. Natural log of 0.88 is 30K. The log of 0.88 divided by 30 is K. Phew. Why did I say phew? K is negative. Because the body's cooling, so it better be negative, right? Otherwise your body's heating up and that would be not ideal. I get negative 0.004, I think. Oh man. 26111-ish. There. Let me just check my 1, 2, 3. Okay. I still haven't changed it so it doesn't give me scientific notation all the time. It's okay. Makes me practice. Okay, so now let's see what we've got here. T of t is 25 e to the negative 0.0042611. I'm going to store this and I'm going to make a note to myself that I'm going to store this in A so I can use the entire value. And usually if I store stuff, then I just make a note of it. And then even in your calculations, you could just say store A, or at least with me, that's fine. But now it's understood that I'm using, even though I'm not writing out all the values, I'm going to use them all when I use store A. Times t, whoops, times t plus 60. Now we wanted to solve for t when the temperature was 98.6. I'll do it up above. Want T of T equal to 98.6. 98.6 is 25 e to the 0.00426 t plus 60. 98.6 minus 60 is 38.6. And that's where that familiar number came from. Okay, that's okay. 25 e to the negative 0.00426 t, but remember I'm using all of them because I stored them. 38.6 divided by 25 is, in order to get at that t, I need to get the exponent on its own. And it works out to a nice number, 1.544. So I'll use that. Is e to the negative 0.00426 t. Now I can take the natural log again. Same trick. 1.544 is, I'm going to jump straight to it without writing the log. Bold move. Negative 0.00426 times t. Which means that t is the natural log of 1.544 divided by negative 0.00426. But I am going to make a note here that I'm actually going to use what's stored in A. So then the natural log of 1.544 divided by A. I get t is negative 101.9396844. Hours earlier.
4.26 to the negative 4. Yeah, to the negative.
Did I? For here?
Yeah.
What did you get? Negative. Oh, another bump, huh?
I had like just negative 1,019 minutes, and then that it only drops.
Oh, I guess t is in minutes.
Drops 2 degrees, 3 degrees in half an hour. That number seems very small to drop that amount.
Yeah, but it's exponential, so, and it's decaying.
I got your value for K.
Maybe it's just a matter of where did we get K from? Let me run that again. The log of 0.88 divided by 30. Still get negative 3. I think. So then here, this is 101 point, well, let's just call it 102 minutes. Roughly 102 minutes.
Oh, yeah, I got it.
Oh, nice. Before finding the body. What a relief. Something makes sense. Did I move it in here yet? Oh, 6 pages. Empty. Okay. There was another one that I wanted to do, but also erratum time, not 4.5 times more energy. The order of magnitude is 4.5. And if I could have seen the chat when I'm in class, would have caught it earlier. Oh, I can't even spell or think today. Magnitude, which means 10 to the 4.5. And 10 to the power of 4.5 is 316227766. This is another one that we put off, but we're gonna do it.
Can we just go back to that body decay one?
Yes.
For a second, and theory of it? I don't feel confident in being able to set that up.
You got it.
You could go through like, you don't take the initial value, first you take the ones they give you, and at the time and time find K. and
Yeah.
then Take the initial and put that K in to find T.
Yeah, so the I would say the main trick would be to let T of 0 be the time where you found it. Whereas initially when I approached it, I wanted to make T of 0 the time of death.
Right.
But then it makes it harder to approach. So then I had to rejig and say, okay, well, what if I take it relative to when I found the body? I can still go back in time, right? And so that's okay. So the key is going to be that you need some sort of T of 0, right? And so if you don't have a T of 0, then you don't get this nice cancellation here, right? So your first thing is to establish, well, what's my T of 0 value? Because then you're going to get e to the power of 0, which is 1. And so this is going to go away, which means you don't have to deal with the k anymore. Otherwise, you'd have 2 variables in there still, and they would just haunt you, right? And so this is the way, right? And so here, we use T of 0 since e to the k times 0 is 1.
The 82 is how you found the rate.
Yeah, so then we move on to the next part. So here we have A, so that's good. And then now if we set up our equation, what's left is we still don't know what K is. So then we need to know another time point, right? Where it's not going to cancel the K anymore. And so then you're going to need a second time point, which in this case is 30. And we force it to be 82, and then you're able to solve for K.
Solve for A with the initial time.
Yeah, solve for K.
With the second time.
Yeah, and then solve for
T.
T with the goal temperature.
Yeah.
Tricky, but got it.
So you look for the initial for that initial temperature or whatever it may be. Word problem.
Yeah, so it's true. So what's sneaky is for exponential functions before, we haven't had to deal with this surrounding temperature, right? So then we would just let 98.6 be the initial value. But here we've got the surrounding temperature going on, and so it doesn't work the way that we're used to. But now that we've worked on this, do you want one similar on the final exam, maybe. Maybe, maybe, huh? It is, it's very tricky. It's making you run through all kinds of things, right? And so, it's a good question. So it's worth figuring out how it works. I might change the degrees and the times, but how about I promise to use this exact sentence structure, different values, which I think I'm pretty good for doing. Test 2, case in point. I've seen this before. I know you have. Okay, good. Another one I put off, and maybe I'll put it on its own page, because we also need the MMS formula. So again, I want you to try to work through it, and then we'll do it together. Oh, but let's see here. 10 times S of the second, or of the first one. We'll start there. And even though you have the value for S0, I would just leave it as S0, because then you can cancel it a little bit easier. Otherwise, it's tempting to multiply it out, but you don't have to do that. Good. Nothing wrong with it. What's your approach going to be? You have one of the M's is 3. So you can use that to solve for S in terms of S0. Right? And then you have your S, which you can use to solve for M in the second one. Yeah, I actually don't know anything about this stuff, but it's all we have, so I have to assume that it is. Energy? Question mark? That's an assumption I'm making. I don't actually know. I'll start listing. Earthquake 1 has a magnitude of 3, which means that m equal to 2 over 3 times the log of s over s0 is 3. I'll do it in many steps, I guess. Multiply that 2 over 3 to the left-hand side because you want to get at the log. And so you get 9 over 2, which I'm going to go to 4.5 right away. Is the log of s over s0. To get at what's inside the log base 10, we have to raise everything to the power of 10, but do it to both sides. So 10 to the 4.5 is 10 to the log of s over s0. The reason we did that, though, is to drop these out, right? The same way that we get at something in the exponent by taking the log of it, right? We can get at something inside the log by raising it to the same base. So now I have 10 to the 4.5 is s over, tried to save space, but because it's virtual space, so maybe it doesn't matter. Which means that s is going to be 10 to the power of 4.5 times s0. Now we know what s0 is, but I'm just going to keep it as s0. So this is the S of earthquake 1. Now earthquake 2 has an S of 10 times 10 times, and I'll denote it by S1. Maybe we'll do this. S2 is 10 times S1. But S1 is 10 to the 4.5 times S0. I've got the same base, and this is technically to the power of 1, right? 10 to the power of 1 times 10 to the power of 4.5 is the same as 10 to the power of 1 plus 4.5. Times S0. So I get 10 to the power 5.5 S0. So now I have its S, which I can solve for M again. M is 2/3 times the log of S over S0. So now we have this value as our S. So M is going to be 2/3 times the log of 10 to the power of 5.5 S0 divided by S0. And that's the reason that I kept this S0, because then it can cancel out. Because I'm multiplying, which means I have 2/3 times the log of 10 to the power of 5.5. Log properties, right? Log base 10 of 10 to the 5.5. It's just going to drop out to 5.5. Two over 3 times 5.5. And these are going to cancel-ish. Well, I mean, technically, what are you doing? You're using the log property that log base 10 of 10 to the 5.5 can be rewritten as 5.5 times the log base 10 of 10. Okay. This is the same as 5.5 times the log base 10 of 10. What to the power, or 10 to the power of what equals 10? 1, which means that this is equal to 1, right? Is the property that we're using, technically. But it's okay if you just want to go, well, yeah, straight from here to here. It's okay with me. Right. Now, 2/3 times 5.5 puts me at 11/3, or roughly 3.67. Ten times more energy equates to 0.67 increase in the magnitude, the MMS. I don't know what, can't remember what it stands for. Whew. All warmed up. There's just the one last thing that I wanted to show you in this chapter, which I hope you've enjoyed, because we're doing a little bit of trig at the end, which, well, I don't like trig, so. I know there's two camps. All my friends love trig, so they teach calculus and stuff. Oh, you gotta know this stuff, it's so important. And I even talked to Allison, because we have to do trig, but I asked her, I was like, is there an application where you would use trig? So SOHCAHTOA, that kind of thing, right? And she thought about it. She's like, maybe something obscure, but no, they just need to be really good at algebra, which is what we've been working on. So I did post this this document that I found on flow duration analysis, which is something that Allison showed me that you guys do, where you draw it on the log paper or whatever it's called. Or maybe you just call it log paper. And so what I wanted to do is, let's see if it opens. No, this is the only reason I brought my laptop today. Okay, so I did post a little Excel spreadsheet of the example that she showed me that I took a picture of. And so I just transferred the data in there. Now what I want to do is see if I can usurp. Okay, I can't share my screen because Excel on the iPad's it's not ideal. Okay. Oh. Okay, turns out it's not happy with me. And I have to jump back in. Now, one of the things I would warn you about is that I know nothing about flow rates or anything like that. I only know about logs. Okay. Sorry. Okay, share my screen. Close this. I already let it. Okay. Blow it up. So this is just information from the slide. How do I make this? Oh, well, you'll just have to put up with it. From the slide that Allison showed me. So you've got some minimum, I guess I can't use this, a minimum flow rate, I don't know, at some location. I made up the locations just to show that they're not just sorted automatically. We would have to do that, but you can use Excel to do that relatively easily. And so we've got all these flow rates, and what they do is to figure out the probability. So it is a probability in the sense that it's the proportion of flow rates that are greater than it. Okay, so in the second tab, sorry, what was that?
Oh, I just wanted to. I guess this is the 7-day little flow chart.
Yeah, I think. I just wanted to show you the logs. And so what you do is you get your minimum flow sorted, and it has to be from largest to smallest. Now, you can do that by, I don't know, there's lots of ways, but you can hit the sort largest to smallest, which it already is in this tab. You want to expand the selection, otherwise you lose the location that's attached to it, right? And if you care about that, then you have to expand the selection, which is the default. I'm assuming you've worked quite a bit in Excel in your courses already at this point? No? Okay.
How are you able to edit this on your Mac? It's the Okanagan license, whatever, it does not let you edit anything on any Microsoft apps on an Apple computer.
Oh,
Do you have like a different license? Are you not on the school license?
no, I am on the school one. That's weird.
Yeah. Like I can open documents, but you can't do anything.
Oh, that's so annoying.
It's like contacts, admin.
I mean, it drives me bonkers how people are still like, oh, if you're on a Mac, oh no, the world doesn't work on a Mac. Well, it does. It works great. And so I don't, yeah, that's so bizarre. Maybe it's because I made it. Are you able to open it and save as something else and edit it? Edit it?
Because every time I open it, it's like, oh, contact your admin for help.
Weird. But you're able to see the values and stuff?
Yeah.
Okay. I guess, yeah, so then, yeah, but that's crazy. And I have not had that issue, no. But I'm also only, like, I made this and I'm not grabbing it from Moodle or anything. Well, let's try. Let me try. With the same name at the same time. Okay, so a different alert. I kind of wanted to keep this one open, but that's okay. Don't save. Try again. I've got that power, which is weird. I don't know.
It says read only.
Does it?
Try and put something.
Oh, it does too. Equals a minimum of these guys, maybe? It's a fake read only. That is bizarre. Okay. I'm gonna copy all this and put it in a new tab so we can start from the beginning, and I'm gonna blow this up. Okay, maybe not like. I'm not doing that fancy clean share. It's my entire screen. Okay, so what did we say we had to do? We had to sort these from the largest to smallest. Expand the selection, sort. Then just make sure that the locations follow. And then my serial, which they called, oh, now I have it somewhere else. M. And I'm just gonna make these 1, 2, once it senses a pattern, you can highlight these. And then if you want it to keep going with that pattern, if you trust the pattern that you've made, oops, then you can hover. And as long as you make sure, just because I don't have a pointer, if you're in the bottom right-hand corner and you've got a black plus sign, you can double click and it'll fill until it runs out of data. Yeah. So that's super useful if you're, I don't know, just starting with Excel. Like I said, I don't know where you're at. That's old news. Cool. So now I've assigned basically a rank to each of these. And what we're going to call the probability is gonna be m divided by n plus 1. N is your sample size, and there's quite a few ways that you could do it. I would say the cheapest way to do it is to highlight this column, which is how many data points I have, and then just look down here. My count is 23, but it just counts how many cells are full. So then I remove the label in my head, and so now my count is 22. There's count functions that you could use. There's all kinds of ways that you could find your n, but n is going to be 22. So to do this calculation and only do it once, you use the equal sign, all right, to set up some equation or a function. And so now you need that, otherwise it won't do anything. It's just going to type. And so now I want to take the m from each previous column, right? So for this one, I want m is 1. For the next one, I want m is 2. And then I'm going to go divided by 22 plus 1, just to make it explicit. But you could just write 23, and that'll be a hard-coded 23. So now, if I hit enter, I want to do that for all the values. You can drag it, but that's annoying. So I go to the bottom right-hand corner, I double click. Ta-da! Notice that, of course, these probabilities are increasing as you move down, because they're based off of this rank. And so one of the things that I would say is it is a probability in the way that a probability is a proportion. So all the p's are all the same. A probability is a proportion, is a percentage, or roughly a percentage. And so that's where those probabilities come from. This had serial 1, and so the probability or the proportion of values out of the 23, setting 1 to be the minimum, I guess, is 1 divided by 23. And so now we're going to say the probability of having a minimum flow greater than 90.3 is 4.35%. Moving on, the probability of having a minimum flow of 59.4 or greater is 8.7%, right? Or 0.0869, whatever. Makes sense that these are increasing because just looking at values. Now, like I said, I don't know anything about the minimum flow. That's on you guys. But it makes sense that they're increasing, right? Because if you think about how 90, so if you know the probability of being greater than 90, and then you go down to 59.4, then of course it has to be greater than the probability of being greater than 90, right? Okay, so now we want to plot the flow on our y-axis and the probability on our x-axis. Now, Excel is kind of weird about how it wants the data when you put it on a scatter plot. And so what I'm going to do is I'm going to copy these into a new sheet. And when I paste them, I'm going to make sure that I paste special. I only want the values because remember we did the calculations. So then it's going to try to go back. And so if I paste just the values, now they're not referencing any of the previous cells. So now they're just going to stay, I don't know why it defaults to this tiny font. So I want that on my x-axis. I think it's xy. And I want the minimum flow on my y-axis. Put that there. Put her there. Make these nice. Okay. So I'm gonna make a scatter plot of these by highlighting them. And again, there's lots of ways that you can do pretty well everything in Excel. There's not just one way, but how I do it is I highlight my data and then I hit insert. And then up here, there's a tiny scatter plot. I'm gonna pick the first one, got options. And so now I've got the scatter plot where I've got the probability. And if I was presenting this, I would put axis labels on here, of course. I would have the probability and the flow rate. Now, one of the things or the problems that we see is that it's not necessarily linear, right? And so if I wanted to, I could fit a straight line to this by clicking any of the data points, right click, add trend line. We could play around with the different models, but for now, I just want to use the linear model. What you can do is down here, display the equation on the chart. And I don't know if you have worked with R squared yet. Just like it is a goodness of fit measure. So the higher it is, or the closer to 1 it is, the better your line models the data. So I'm going to display the equation on the chart, and I'm going to display my R squared. When we think about models, right, so this line is a linear model of this activity, I would say it's not doing a great job because it's not capturing these guys, right? And it's not capturing this little guy up here. Now we have a small data set, so kind of flexible, okay? But also the R squared is 71% or 0.7118. So that's not good, not great. Okay. So what we do, and I realized one of the kind of cool things that you could do is, well, you could tell it to change it from linear to logarithmic or exponential and play around with it. But kind of fun is if you click the axis, actually, let's start with the y-axis. So semi-log and log-log graphs. Semi-log graphs are usually you take the log of the response variable, so the log of the y, which would be the log of the minimum flow. You could do that over here in the cell equals the log of this, right? But, and I did that in one of the sheets, but I was playing around with it. And if you click the axis that you want to see in log form, you can right click and you can format axis. And then there's a logarithmic scale down here. Kind of fun. Whee! What effect did that have? Well, it curved our linear model. So that's kind of weird, right? But it also made, if you ignore this trend line, that linear model, the initial linear model, it made it a little bit more linear, right? So now, remembering that the reason we use logs is because we can take some exponential growth or decay and we can kind of straighten it out and make it linear, right? Because the log of a times b to the power of x is the log of a plus the log of b times x, right? So that's a straight line. And so when we do that, right, if we go ahead and we do the x-axis as well, format axis, logarithmic scale, didn't help. that much, I guess. But what can I do? What can you do when you live in a shoe? Add trend line. Now, I'm gonna add a linear model and I'm gonna display both of them, both those values on there. Oh, I wanted up the transform data. It just did the same thing. Fine. Fine. Add trend line. And I'm going fast, I know, but also it's just for fun. So let's see. Fit a logarithmic model. Display the equation, display the r squared of this. Where did it go? Can I move it over here? I wanna.
Can you add a linear based on just a certain amount of data points? Because that's usually what we have to do with two separate linears to find that point.
Yeah, I don't know how in Excel. Because you would have to do a piecewise function. Now, I think that you can set the axis, and then you'd have two lines, but I feel like you could break it up by the axes, but that's beyond my my skill level. I'm sure it exists out there. Okay, it's really hard to see, but this line here, it's got some curvature down here, it looks like to me. Or maybe I'm just going cross-eyed. Oh. Right? It's not supposed to. Maybe it doesn't. But our r squared is way better. 0.9284. But now, right, you've got different coefficients because we're now working on the log scale. Let me try. Oh, you know what I can do? Maybe. Can I change the color? Color. There. What if I fit an exponential model? And I'll make it green. Pretty similar. And what a mess I've made. I'll move this over here. Not very good r squared for the exponential model. So I would choose the logarithmic model based off of r squared alone. Fun, right? Could kick it old school. I always make a copy and then I paste it in. Oh, that's not what I wanted to do at all. Copy. I paste it. Hey, I didn't want to copy the graph. I just want these guys. Keeps doing it. Oh my gosh. doesn't want to do it. Oh, yep. You could zoom in. Take the log of the probability. I'm guessing log base 10. So if you go equals and then log, there's the log, just the log, but the default is base 10, but you could specify log 10 if you want to. But this log function, you can specify any base, but I'll use this one of the probability. And then if I want to do that for all of them, all right. So now I've got my x-axis logged, the log of the flow is the log of this little guy. So now what you can do is you could make a scatter plot of these guys. And it won't have the adjusted scales. But now you've got way more of a linear function. And what we can do is we can add a trend line to this thing and make it linear. And then just remember that the interpretation is now in terms of the log of x and the log of y, right? Which is a little bit trickier. But you have an excellent R squared of 0.9204. And then you can fit a y equals mx plus b model to this thing, right? Where y is the log of the flow and x is the log of the probability. And that's logs. You did it. If you have any questions, let me know. Otherwise, I'll see you on Wednesday, and we'll do a trig sprint. Oh boy. They're yours to treasure forever. And I'll stop this.